So in this lesson and in future lessons, we're going to be investigating acids and bases quite a bit. However, we need to distinguish between strong acids and bases and weak acids and bases. So first of all, I have a list of 7 strong acids. They include hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and then sulfuric acid. You need to memorize all of those. Your strong bases are a little bit easier to memorize because it's your group 1 metal hydroxides and then calcium, strontium, and barium metal hydroxides. Now, why do we need to memorize these? How are strong acids and bases different than weak acids and bases? Well, strong acids and strong bases dissociate completely into their ions when they're put in solution, okay? So another way of investigating this is talking about whether reactants or products are going to be favored. So if we think about it, the stronger an acid or a base is, the weaker its conjugate acid or bases. So for these strong acids and strong bases, their conjugate acids and bases are going to have negligible acidity or basicity. So again, how does that help us to determine if reactants or products are favored? Well, if you have an acid and a base in the reactants that are strong, that means that the reaction is going to proceed to the right more than it proceeds to the left because its conjugate acids and bases are going to be weak, and therefore the products will be favored. In contrast, if your acid and your base in the products are stronger, meaning the conjugate acid and base are stronger than the acid and base themselves, what that means is that the reactants themselves are going to be favored. So the equilibrium will favor the left-hand side. Okay, so let's actually look at the dissociation of a strong acid. So when a strong acid dissociates, we don't actually need to use an ice chart because all of our acid is going to dissociate, but let's actually look at it and see how the ice charts work because it still works with ice charts. So here I've got perchloric acid and it's going to dissociate completely into its ions. It's going to dissociate into hydrogen ions and perchlorate ions. And so I'm going to create an ice chart. Okay? And the problem tells me that I start with 0.040 molar of my strong acid, and I don't have any of my hydrogen ions or my perchlorate ions. So the change that's going to occur is going to be minus 0.040 for perchloric acid. Now the reason why is because, well, based on the definition of a strong acid, 100% of it is going to dissociate. And therefore, I already know my X. It's negative 0.040. So it's going to be plus 0.040 and plus 0.040. And so at equilibrium, I have none of my perchloric acid, and I got 0.040 of my hydrogen ions and 0.040 of my perchlorate ions. So what I can do to calculate my pH, it's actually quite easy because right now I already know my concentration of hydrogen ions at equilibrium. It's 0.040. And so what I can do is just take the negative log of 0.040 and that will give me my pH. So my pH equals 1.40. And the reason why it's the 0.40, remember, 2 sig figs gives me 2 decimal places for pH. So that's for strong acids. Same thing for bases, except it would dissociate into hydroxide ions and then the metal ion, and you'd simply take the concentration of your hydroxide ions at equilibrium to find POH and then pH. So really not bad. Let's look at weak acids, because for weak acids, you have the complication that not all of the acid is going to dissociate. So there are 2 different ways of writing a weak acid dissociation. The first one, notice I've got HA, my acid, and it's going to be dissolved in water, and it's going to form hydronium ions, and then your other anion. Now, that's one way to write it, because remember, for an acid, it donates a proton, or the other way, which I prefer to write it, is simply your acid dissociating into its ions, like what we did for the strong acid in the previous slide. We will interchange the term hydrogen ion and hydronium ion because notice, other than the water, which we'll ignore for ice charts, those are the exact same reactions except for the fact that you have hydronium in the top one and hydrogen ions in the bottom. So I tend to use the bottom one. Either one is perfectly fine. Let's look at an example. We are going to calculate the acid dissociation constant, your Ka, when you're given pH. So in this example, it tells me that I have my acid. So I'm going to write out my reaction right away. I've got my acid dissociating into hydrogen ions and then that anion. So I'm going to create my ice chart like before. My starting concentration is 0.10 molar, so I'm going to put that there, and I don't have any hydrogen ions and I don't have any of that anion. And so the change that I'm going to see now, instead of being able to just say minus 0.10, I can't because this is a weak acid. So I've got to subtract x, add x, and add x. And so what I end up getting at equilibrium is 0.10 minus x, x, and x. So normally the next step that I would take would be to write my equilibrium expression and therefore calculate my acid dissociation constant, or my Ka. However, here's one important point. Notice it gives me, this problem gives me my pH. It tells me that my pH equals 2.38. So what I can actually do first is take 10 and raise it to the negative 2.38 and calculate my concentration of hydrogen ions. And what I end up getting for that is 0.0042. Now I wrote x equals 0.0042 because that is your concentration of hydrogen ions. And so now I know my concentration of hydrogen ions, I know my concentration of my anion, and now I know I can figure out by subtracting the concentration of my acid. And so I'm going to plug that into my equilibrium expression to calculate my Ka. So my Ka equals my concentration of my hydrogen ions times my concentration of my anion all over the concentration of the acid. So now I know my Ka equals, well, the 0.0042 times 0.0042 divided by the concentration of the acid, which by subtracting I find is 0.0958. And so my Ka for this is going to be 0.0018. And that's it. Now, instead of solving for Ka when I'm given pH, what if I need to calculate the pH when I'm given my Ka? Let's look at an example. Here it gives me acetic acid, and it gives me my Ka and asks for the pH. So I'm going to first write the acid dissociation reaction. So I've got my acid dissociating into my hydrogen ions and my acetate ions. I'm going to ice it. I know the initial concentration, 0.30, and then 0 for hydrogen ions and 0 for acetate. It's going to change by negative x, so minus x and then plus x, because again, this is not a strong acid. And so at equilibrium, the concentrations will be 0.30 minus x, x, and x. Okay. Now what I need to do is I need to write my equilibrium expression. And so I know my Ka here is 1.8 times 10 to the negative fifth, so I'm just going to plug that in. And that's going to equal my concentration of hydrogen ions times my concentration of acetate ions all over my acetic acid concentration. So now I can plug in my variable. So 1.8 times 10 to the negative fifth equals x squared over 0.10 minus x. Okay? Now, here's the thing. Based on the rule of 100, if you take 0.30 and divide it by 1.8 times 10 to the negative fifth, that's going to be greater than 100. Therefore, I can ignore the minus x right there, and I can easily solve for x now by multiplying 1.8 times 10 to the negative fifth by 0.10 and then taking the square root of that. And so I get x equals 0.0013. Now you might be tempted to want to be done at this point. However, notice that's just my concentration of hydrogen ions, not my pH. So to find pH, what you need to do is take the negative log of 0.0013, and what you get is 2.87 for your pH. The last concept I'm going to go over is polyprotic acids. Now, polyprotic acids are acids that lose more than one proton. And the key thing for you to remember with these polyprotic acids is the fact that it's a lot easier to remove the first proton from a polyprotic acid than to remove the second. And so if I ask you to find the pH of a polyprotic acid, since you are removing two hydrogens, you might be tempted to incorporate both of those in finding the pH. However, because you'll lose so many more hydrogen ions in the first removal, you only look at your first dissociation reaction. You don't look at the removal of a second proton. So let's look at this. Here's my example, okay? It gives me the initial concentration of carbonic acid, and then it asks what's the concentration of CO3 2 minus, and what's the pH, okay? So the first thing I'm going to do is I'm going to set up my reaction. So carbonic acid is going to dissociate for the first one into hydrogen ions and then HCO3 minus, okay? by incorporating what I know with my ice chart, the concentration of carbonic acid starts out at 0.0037, hydrogen ion 0, and then HCO3 is 0 as well. So I'm going to subtract X from carbonic acid, add X, and then add X to my products. And so what I get at equilibrium is 0.0037 minus X, X, and X. So using this and the fact that I know my Ka, my Ka1, I can solve for X. And so X times X, X squared, because that's the concentration of hydrogen in HCO3, all over 0.0037 minus X equals 4.3 times 10 to the negative 7th, because that's my Ka1. Now keep in mind, based on the rule of 100, I can ignore that minus X. And so what I end up getting when I solve for this by multiplying 0.0037 by 4.3 times 10 to the negative 7th and square rooting that, I end up getting 4.0 times 10 to the negative 5th molar. Now that is the concentration of H+. Do note that you're going to have a little bit more H+ with the second dissociation. However, we're going to ignore that when we're calculating for pH. So instead, what we can say is simply take the negative log of this concentration, and we end up getting 4.40. Okay? I would be done, and I could even ignore the second dissociation. However, it does ask for the concentration of CO3 of my carbonate. So what I need to do is I need to mentally note the concentration of my hydrogen ions and my HCO3 because I'm going to plug that in for the next acid dissociation. So I've got 4.0 times 10 to the negative 5th for both of them. And so the second dissociation, HCO3 is going to dissociate into H+ and CO3 Notice the initial concentration of both of those, of the HCO3 and the hydrogen ions, is 4.0 times 10 to the negative 5th because I've already done one dissociation. However, do notice that the concentration of carbonate is going to be 0 because I didn't have any of that. Now they changed the variable, so instead of X, it's going to be Y. Doesn't really matter, so minus Y plus Y plus Y, and there are my equilibrium concentrations. Now I can write my equilibrium expression and use my Ka2 now because this is the second dissociation. And so with that, one big thing that I can do, because based on the rule of 100, I can ignore whenever I add or subtract by that variable. Instead of 4.0 times 10 to the negative 5th plus Y, I can just say 4.0 times 10 to the negative 5th. I'm going to multiply that by Y because that's the concentration of carbonate, and divide that by 4.0 times 10 to the negative 5th. Notice it's very convenient because those 4.0s cancel out, and I end up just with Y equals 5.6 times 10 to the negative 11th, and that is your concentration of carbonate, and you're done. Now, if you really wanted to, you could take the concentration of hydrogen ions in this equilibrium and add it to the concentration in the previous one. However, as you'll notice, your pH is not going to change significantly because the concentration of hydrogen ions at equilibrium for the second dissociation is much smaller than for the first dissociation.